All right, so our challenge is to take a nebula, giant molecular cloud, and go through and collapse it down into a solar system and make it look like our solar system. So we know we have gravity, and gravity is going to take little lumps and bumps and collapse it down. So, problem solved.
Yes, we've seen that before. The trouble is, it might be rather too good. I mean, gravity's going to make every bit attract everything else, so why doesn't the whole thing shrink all the way down to form a single lump in the middle, like a very big star or a black hole? We don't want it to do that. We want a lot of the mass to go into forming a star, but we want some left out to form planets.
Well, I think we can get some clues to that, Paul, if we look at an object like this, not in optical light, because we can't see through all that dust. Let's look in radio. So if we take a radio telescope like this one, this is the Mopper telescope located in the middle of New South Wales, and we can go through and we can look at carbon monoxide. And carbon monoxide has a transition in sort of the radio microwaves, and that will pass right through that cloud of dust and stuff, and we can see what's going on. So here's a picture, and you can see it's not nice and smooth and not just one thing. There are lumps and bumps all throughout this.
And you can use a Doppler shift to measure the velocity of the gas. And what you've got here is a whole group of spectra pointing at the different clumps over here. So each of these blue boxes is a different clump, and here's a spectrum for all these clumps. And what you can see is if you point to a given clump, you've got some gas at this velocity, some gas at this velocity, a lot of gas at that velocity, whole range of different clumps at different velocities. And these velocities are enormous. We're talking of tens of kilometres a second. So it seems that a giant black cloud isn't just a stationary bit of gas sitting there. It's made of a whole bunch of lumps moving at enormous relative speeds. So let's see how that is going to affect the collapse of something like this. So we have a giant molecular cloud, and we want to see how the motions of the different bits are going to affect its collapse. So let's come up with a toy model. Let's imagine the giant molecular cloud is a collection of blobs, all moving with velocities of around 1 kilometre per second. Total mass is around 10 to the 33 kilograms, and the radius is about 10 to the 16 meters, a light year. So how are the random motions of all these different blobs going to affect its collapse? Well, the idea is that gravity is going to pull everything towards the middle, but as it does so, we have to factor in a very important law of physics, the law of conservation of angular momentum. This is one of the three great conservation laws of physics, along with conservation of mass energy and conservation of momentum. What is angular momentum? Well, let's say you have something moving around a pivot. It's got some velocity v, which is at right angles to the direction from the pivot. Angular momentum, written L, is defined as m v, which is only the perpendicular component of the velocity. A velocity in this direction or that direction doesn't count. It's only a sideways velocity, times r, where r is this distance here. And it turns out that that is conserved. Unless you apply external torque to the system, this will always be the same. So what does that mean? Consider this blob over here. As it falls in, mvr will remain the same. The mass is going to remain the same. So what that means is the velocity, at least the sideways component of the velocity, is going to be proportional to 1 over r. So as r gets smaller, v has to get larger to keep the angular momentum the same. So if it starts off with a velocity, let's call it v0 of about 1 kilometre per second, and starts off at a distance r0 is about 10 to the 16 meters, a light year. Then as it moves close in, at some distance r, we'll know that the velocity at some distance r is equal to r0 over r times the starting velocity. So This works okay. When r equals r0, when it's at starting position, that's just 1, so that means the velocity will be equal to the starting velocity. As r gets smaller, this gets bigger, so the velocity goes up, thus giving the angular momentum constant. So that comes from conservation of angular momentum, and it means that as something falls in, the sideways speed will go closer. So if it's falling in, there's a middle of the giant molecular cloud, starts off out here going slower. By the time it's in closer, it must have a much larger sideways velocity. Okay, so that's one thing. The next thing we have to take into account is that when something's moving in a circle, there needs to be a centripetal force, mv squared over r, to keep it in that circle. If it's going faster than that, it will fly out. This is the same thing we talked about in the dark matter part of the course. Remember, if you balance gravity against centripetal force, you get the orbital speed, which is v equals root g m over r. So if something is going that fast, centrifugal force will balance gravity and it won't fall in anymore. So we've got our blob up here, and it's falling in. As it falls in, it'll go faster and faster. So its velocity will go up as 1 over r, and eventually the velocity will reach the orbital velocity. And at that point, it will be in equilibrium. The centrifugal force will balance gravity, and it won't fall in any further. So when will this happen? Let's set these things equal to each other. So we set this equal to that. So we get root g m over r equals r0 v0 over r. Square both sides. So to get rid of the square root, so gm over r equals r0 squared v0 squared over r squared. Cancel one factor of r, then bring the r up here and the gm down there, and you end up with the radius at which things balance is equal to r0 squared v0 squared over gm. So our blob, as it falls in, will stop falling in when it gets to this radius, at which point centrifugal force will balance gravity. So we've got our blob moving over here, centre of the cluster. It'll come in, and when it's at that radius, it will just stay there orbiting round in a circle. What is this radius? Well, we can plug in numbers, r0 of a light year, v0 about a kilometre per second, the total mass, and g, and that comes out as about 1.5 by 10 to the 15 metres. So that's about 15% of a light year. That's pretty big. So what that's telling us is if we have our bunch of blobs orbiting round, they will go in quite a bit, but then they'll all be orbiting in different directions depending what their initial velocity was, but they won't shrink any further. This is about 10 times smaller than their starting size, but it's still an awful lot bigger than solar systems, which are about 10 to the 12 meters. It's 1,000 times bigger than a solar system. So that's an individual blob. So let's say this blob here was originally going like that. By the time it shrinks down, it'll end up going around like this. Let's say this blob was going in this direction. By the time it shrinks down, it'll be orbiting over the top like this. So you get a whole bunch of blobs all shrunk down into a small space, all going at different rates in different directions. They'll collide with each other, they'll bang in. So what will happen is you might have one blob going this way, one blob going that way, another blob going this way, but they'll all smash into each other and they'll average out their speeds. That will partially cancel out the angular momentum, the initial velocity, so eventually it'll shrink down even smaller and they'll all end up with some sort of average motion. So they'll end up as a spinning disk of gas.